Okay, to finish up on our satellite, we're almost done with this chapter, but we said it would take 8 kilometers per second, okay, to get into orbit, and that would keep it at a rate where it's going fast enough that as it falls, it would uh, follow the Earth's curve, all right, and it could speed up. Now, if it speeded up, greater velocity, it would get farther away from the Earth, okay, and then it would take a lower velocity to maintain that orbit. But if if it increases, it's going to get farther and farther away up until it gets to 11.2 kilometers per second. And if it does that, it will continue to pull away from the Earth and eventually leave get far enough away from the Earth that there's not enough pull of gravity to keep it in orbit around the Earth. Okay. Now, once again, you can't escape the Earth's gravity because any two objects that have mass will have an attraction between them, and no matter how far away you get out here, but you're no longer going to be. They're not going to be a strong enough force to pull you into an orbit. So you're free from the orbit of the Earth, and you'll break free of that at 11.2 kilometers per second. If you go faster than that, then you will escape from that. All right. Notice that if a rocket is taking off from the Earth, okay, it does not just go straight off like that because there is the pull of gravity. Actually, I should put it straight up from the ground. There we go. That would be a little bit better. Okay, it does not just go straight up because gravity is pulling on it and it's trying to escape that pull. So it tends to be more of a curved path taking off, but eventually it will break free of the Earth's orbit. It will not be orbiting, and then it can continue to travel wherever. So like when we sent ones to the moon and whatever, they had to calculate that, what kind of curve would it take as it escaped the Earth's gravity and to get free from the Earth. Okay. Now, if it's in between 8 kilometers per second and 11.2 kilometers per second, then it will stay in orbit, all right, around the Earth. And the orbit around the Earth is called a period. A period is just something that repeats. So if it's circling around here, it will come back around and it will repeat and come around the same thing. So how long it takes it to go one cycle before it repeats would be considered a period. A pendulum. If you have a pendulum, and it's swinging like this, and then it comes like this, and then it comes up on the other side like this, and then it swings back here and swings back here. Once it repeats, it's back to where it started. That would be this first one. That would be one period of a pendulum. So a period just means how long it takes until an object repeats it. So the period of satellite, in this case, is how long does it take for it to go around the Earth. Okay? Now, as you get farther out from the Earth, it takes a lower velocity to stay in orbit. So we said like if one was going in this orbit and begin to speed faster, get farther and farther from the Earth. But once it gets into an orbit, if you want to keep it in that orbit, you need to keep it at a fairly constant speed, not a constant velocity because you are going around the Earth, but you would have to keep it at a constant speed. And so you would hit the speed. The speed needed to maintain this orbit is less than this one because gravity is not pulling on this one as much, so it doesn't need as much. Now, also though, if you draw these whole circles around here, which one's going farther? Well, it turns out that this one out here on the outside is going farther, and so it's going farther at a slower velocity, so guess what? It's going to have a very long period. It's going to take it a long time to get around the Earth, whereas the closer one has to go faster to maintain its orbit, and it's on an inside track, just like the inside track of a running track. It's going to go less distance. So if it's going faster, less distance, it's going to have a lot shorter period. If a satellite is in what we call low orbit, above the Earth's atmosphere, but just above the Earth's atmosphere, it's going to have a period of about 90 minutes. So it's very quick. Every hour and a half, it would completely circle around the Earth's, completely around the Earth. Okay, that's very, very quick. Now, if it's 5.5 miles above the Earth's atmosphere, then it would have a period of 24 hours, which means that its period would be exactly equal to the rotation of the Earth, which means that as it goes around, the Earth's rotating at the same speed, so it would stay right above the same location on the Earth. This is called geosynchronous. Geo meaning Earth, and synchronous means it's synchronized or going at the same speed of the Earth, and that means the satellite would stay over the same location, which is good. If you have a satellite TV station and you're down here, you want it to stay with you so that as the Earth rotates, your satellite's also going with you and you're getting your coverage. If it was going faster, then it would end up getting away over here, and then eventually, as it gets farther away, you would start losing your signal, or if it was slower, it'd start falling behind, and once again, you'd lose your signal. So geosynchronous is when you want to keep the 5.5 miles above is where you would keep it would keep it at a point where it would stay above the same point, and that's a very important thing. As you get farther and farther out, it would take even farther. For example, the moon, which is way out there, is 27.3 days, almost 28 days. Usually we just say, but 28 days a period to go all the way around the Earth. All right. First of all, like I said, 5.5 miles would give you a geosynchronous orbit. Actually, it's 5.5 times the radius of the Earth, or the distance from the surface of the Earth to the center of the Earth. 5.5 miles would barely put you above Mount Everest, so that would not be good. But if it's 5.5 radius is of the Earth, or the distance from the surface to the center, okay, 5.5 times that will give you that period that matches the Earth's rotation. Now, if we look at the orbits of a lot of natural satellites, for example, all the planets going around the sun and so forth, then notice that instead of a nice circular orbit, usually they are more of an ellipse. In a circular orbit, if you have something going in a circle, or pretend that's a circle, and here's the Earth, okay, the force of gravity throughout the circle is going to be the same, because you're always about the same distance from the Earth. Therefore, your speed can stay about the same, and the pull of gravity stays about the same, and the potential and kinetic energy stays about the same. All right. However, if an object is going, if a satellite is shot into the atmosphere at a speed greater than 8 kilometers per second, okay, and it will often form an elliptical. A lot of planets and so forth will form an elliptical shape, or ellipse is the shape, and then it's called an elliptical orbit. Okay, so as it goes, as it's leaving, it has a high acceleration, and it's pulling away, getting farther away from the Earth, because it's above 8 meters per second, so it's actually getting farther away from the Earth. But eventually, as it gets farther up here, eventually the pull of gravity gets weaker, but so does the velocity gets weaker, and the velocity gets weak enough that the pull of gravity starts pulling it back to Earth. Okay, and so as it's coming back around toward the Earth, now it's getting closer to the Earth, so the force of gravity gets stronger, it starts speeding up, speeding, it's the closest, so it's going fastest right here, and then it comes back around, and it's going really fast at first, so it pulls away from the Earth, but as it gets farther away, it's slowing down. The force of gravity is getting less and less, but it's slowing down to the point that it stops, and then the force of gravity, even though it's weak, is still enough to pull it back into orbit, and it keeps coming down, and it gets closer, more gravitational force, it speeds up. Okay, and if you think about this, if you think this is up and this is down, it's kind of like throwing a ball up in the air. If we throw a ball up in the air, it goes up, it slows down, and then it starts accelerating back toward the bottom. Well, you're basically kind of doing the same thing here, is that as it's close to the Earth, it has more gravity, so it starts slowing it down, pulling it back toward the Earth, it slows it down until finally it slows it down enough. Even though there's not much gravity, there's also even less speed, and finally it loses no speed, like at the top, or ball at the top, where it stops, and gravity pulls it back in. Now as it comes down, this is like a ball falling down, it's getting closer, gravity's pulling it harder, it starts speeding up, and then it's still speeding up, but then it starts slowing down, and gravity pulls it back in, and then it comes back down. Okay, and so it's similar to that. And so we would say that it would have the most kinetic energy down here at the bottom. As it gets farther away, just like something above the Earth gets farther away, then it has more potential up here. So it has the most potential here, and then it speeds up. It has the most kinetic energy that's coming down here at the bottom. And it will just continue to do this orbit like that. And so since there's a different distance, therefore a different force of gravity, the speed and the distance from the planet will vary all the way throughout the orbit. Whereas, like we said, a circular orbit, it's always the same distance, it's always about the same speed, and so forth. All right, so that should pretty much finish talking about gravity and satellites, and we'll see you in class. Have a good week.